All right, next we're going to talk about non-ideal batteries. So not all batteries are perfect like we see in the problems where you get a voltage and that's what voltage you get out. Your batteries will be rated for some amount of voltage, but the amount that comes out is always going to be a little bit less because of what's called internal resistance. So the way you find out internal resistance is the terminal voltage of your battery. So that's either V-term or V-bat. The amount that comes out is going to be equal to the electromotive force, got to make them fancy, electromotive force minus the current through your circuit times the internal resistance of your battery, so R internal. So let's see what this looks like in a problem. Over here, this is my battery, this whole thing. The part here that says battery that's supplying the electromotive force and the internal resistance of it. I've got a battery that's rated for 12 volts of electromotive force with an internal resistance of 0.5 ohm. It's in series with a 65 ohm resistor, and what we've got to do now is find out what the current is. So I want you guys to go ahead and try to find the current in this circuit, then try to find what is the voltage difference between the exit of the battery and the entrance back into the battery. Find what that is. And then finally, I want to know how much power is dissipated on this resistor and this resistor. So you're going to need to use the first two sections of notes we had for this circuit section. Take a minute, pause the video, try to solve for them. When we come back, we'll do it together. All right, so what we should know is that our total electromotive force is going to be equal to the amount of voltage that's used up here and the amount of voltage that's used up here. So we'll call that like V internal plus VR. That works for me. So we need to solve for what those are. Well, since these guys are in series, there's only one pathway from this power source through both of the resistors. They should both have the same internal, they should have the same current through them. So V equals IR, so it'll be I 12 volts equals I times this internal resistance of 0.5 ohm plus whatever my current is times 65 ohms. When I plug all that in and solve for I should get 65.5 I equals 12. So I'll divide 12 by 65.5. And when I do that, I am going to get a current of approximately 0.183 amps. Cool. So now we can use that to find out for what the terminal voltage is. So terminal voltage is just the amount of voltage that's left over when you leave. Some of it gets used up on there, so we just subtract 12. 12 volts is our total electromotive force, minus the amount of voltage that gets used up in there. That's IR. I is 0.183 amps. The resistance of it is 0.5 ohm. And when we plug that in, it's going to be very close to our total amount, but it's not going to be the exact same. We're going to end up with 11.91 volts left over. That's our terminal voltage. Now, finally, we need to find out what the power is. If you guys remember, power is, we have three different ways of writing it. In this one, I think the one that's going to be most useful, since we have I and R already on here, we don't want to have to solve for what voltage is on there, even though technically we have it. But let's just do power equals IR squared. So power equals IR squared. We'll do two different ones for our battery. Or is it it's I squared R, my apologies, I squared R. I was like, wait a minute, that sounds wrong. So we'll do for the internal resistor, we'll square this guy times 0.5 ohm. Hopefully this is, still on the screen. When we do that, we get a power for our internal resistance of 0.02 watts. When we do the same thing for our resistor outside, we have the same current, 0.183 amps. We'll square it, multiply it by 65 ohms. This time, it's going to be significantly larger. When we do that, we get 2.18 watts. Cool beans? So now we know how to solve for power. Now, one thing I want to note is this equation right here is not on your formula sheet. That's because it's fairly straightforward using concepts they've already given you. What you're going to Come on, man, I'm moving around. I'll be back in a half second when the lights return. As I was saying, this isn't on your formula sheet because it's fairly straightforward from the equations you've been given. The amount of energy, or sorry, electromotive force you have left over is going to be the total amount minus how much you use up going across the internal resistance of the battery. All right, now, so for finding power that's dissipated in a battery before it ever leaves, we're going to have to use the terminal voltage. Now, what we're going to solve for right here is for the power that's left over coming out of the battery, but an internal term for it is going to be the amount that's dissipated in the battery. So what we're looking at here is power is going to be equal to the I, which is current, times the electromotive force, because the terminal voltage of a battery is electromotive force minus the energy that gets used or the voltage drop in the battery. So that's going to be I, again, times the resistance of the battery, so the internal resistance. This part right here, times I, is going to be the amount of energy that's lost inside the battery. This total amount is going to be the power output of the battery. So if we distribute this, what we end up with is I epsilon minus I squared R internal. Again, I don't believe this is one that's on your formula sheet, but it should give you the idea based on the fact that it's fairly straightforward. Power that comes out of a battery is just going to be equal to the total power minus how much gets used up in the battery. So now on this one over here, we've got two batteries facing against each other. I've got one with a voltage of 4, one with a voltage of 2.1. This one has an internal resistance of 3 or 1.3, and this one with an internal resistance of 1.8. What you guys are going to need to do is figure out both the direction and the magnitude of current, so whether it's clockwise or counterclockwise, and then how strong it is. Then once you're done, I want you to make a chart that shows me total voltage at each section of the chart. So that's each chart element as it goes through the battery, the internal resistance of the battery, point A, internal resistance, battery, B, C, all that. Same, you got the idea. So take a second, pause the video, try it out on your own, and then we'll come back together and do it. All right, first thing I notice is that this battery is a higher voltage than that battery, meaning it's going to overpower it. So our current should be going clockwise. All right, and the next thing that I'm going to do, basically I should know that as I go through the whole circuit, I should end up back at 0 volts. So I start at some value and I end up at 0, meaning that when I cross back over this battery again, all of my voltages should add up to 0. So what I'm going to do is I'm just going to use the voltage at each point to figure out what my current is. And I'll just start right here at epsilon 1. So here's my electromotive force 1. How do I do this? There we go. My brain was dying on how to make the shape. So that guy's voltage. Now it's positive because we're going across it this way. Now I'm going to cross this guy. Voltage is being used up there. So what I'm going to say is minus, and that's going to be, to find voltage at that point, it's going to be V equals IR, so resistance times current. So that's 1.3 ohms times whatever our current is. I'll go ahead and just put the numbers in to make things simple. Okay, my next step is through this internal resistance, so that's minus 1.8 ohms times whatever the current is. Then I'm going to go across this battery, but I'm going across it the opposite way, meaning I'm going to have to use up some of my voltage to go across it. When you go in the opposite direction of a battery wants you to go, you're going to lose the voltage going across it. So that's minus 2.1 volts. Then I'm going to come down here to this resistor, minus 5.5 ohms times the current. And when I do that, I should end up with 0 volts because when I start here, I have 4 volts to use. When I get all the way to this end of the battery, I'll have 0 volts. Then I'll cross back over those 4 and I'll be back up to 4 like I said at the start. So let's take a look at what this comes out to be when I combine like terms. So I get 4 minus 2.1 volts on this side is going to be equal to, my I terms will be over there, that's I times 3.1 plus 1.8 plus 5.5. And remember, these guys go from negative to positive because I move them over to the other side of the equation. So basically what I'm going to have is this divided by that gives me I, and when I do that, I get I has a current of 0.22 amps. Cool, now that I can do that, I can actually just go through and solve for what all of the voltages are. So if you haven't already, go ahead and use this current. Just plug in for this, you get a voltage, this you get a voltage, and this you get a voltage. Then you'll have a voltage at every single spot on the chart. Go ahead and try that. When we come back, I'll have all of them filled in and we can talk about it. Okay, my chart's a little rough here, but hopefully you guys get the idea. When I cross from the battery, I'm going across my first epsilon 1, the epsilon of this battery. When I cross it, my EMF raises me up by 4 volts because I'm going in the direction the battery wants me to go. So I'm gaining voltage. Then I lose some of my voltage by crossing the internal resistance of the battery. I go down. Across A, there's nothing happening. It's just measuring what the voltage is, so I should remain flat. Then when I cross the internal resistance of the second battery, it's a little bit higher of resistance, so I drop a little bit more. Still, I'm above a value of 3. Then I come over here, I'm going to drop by 2.1 because I'm going against this battery. So my EMF is dropping by 2.1. B, again, there's nothing going on there. When I get to this resistor, the remaining voltage is going to drop because there are no other circuit elements after that because C is just a point in the circuit. The wire has no resistance. And that's all we've got today on resistance and batteries.